Let us think about the structure of KMnO4. So KMnO4, the structure of KMnO4. So here it's being KMnO4, K is metal, right? So what happens? It gives one electron and becomes K plus. Where it gives it gives one electron to this species, that is M1O4 species. So M1O4 becomes minus. So transfer of one electron. So this metal gives one electron, gives to the M1O4 species. So an ionic bond is established here. An ionic bond is established here, right? So here, let us go for the structure. That is K plus and MnO4 minus. So manganese MnO4. O4 minus. One O is having the negative charge. So that will be having a single bond. The other three oxygens will have double bond. The other three oxygens will have double bond. Now, do you remember the structure? What is the structure is called? Tetrahedral structure. Tetrahedral. This structure is called a tetrahedral. What happens here? The negative charge is one oxygen left. This negative charge comes down here so that this bond backs up to this oxygen. This gives rise to a structure. Here double bond O now, and here M1, here single bond O minus, and double bond O, double bond O. And then what happens here? This electron comes here and this bond shifts over here. So here M1 double bond O, here double bond O, here single bond O minus, here double bond O. And then this electron comes over here and this electron shifts over here. So that will be double bond OM1, here O minus, and here double bond O, and here double bond O. And this gives rise to another structure. That is, the electron comes here and this goes out there. This gives rise to another structure like this. That is, I'm writing here. This will be clear for you. That is, again, MnO minus, here double bond O, here double bond O, here double bond O. So this is similar to this first structure. This is similar to this first structure, right? So how many structures are possible here right now? So this is 1, this is 2, this is 3, and this is 4 structures. 4 structures are possible. Got it? So let me write again here. Manganese K plus M1O4 minus. So M1 will be at the center and O minus, and this will be in tetrahedral structure. This will be tetrahedral structure. And how many resonating structures are there? Resonating structures, 4 resonating structures are there. 4 resonating structures are there. And this structure is called tetrahedral. And what is the bond angle between these two? Tetrahedral bond angle. Bond angle are equal. That is tetrahedral bond angle. This is a common question. They'll give a tetrahedral structure compound without giving the structure, and they'll ask for a bond angle between them. That is 109 degree 28 minutes. So the bond angle will be 109 degree 28 minutes. So this is tetrahedral bond angle. Have a look over this. This is important. Now let us go for the resonating structures, proper resonating structures. So this is what we had done here. So listen here. First, the negative charge lies in this carbon atom, and second, the negative charge lies in this carbon atom, and third here, and fourth here. So the negative charge, it moves on, it goes on movement, it is not stable. So that 4 different resonance structures are possible. So that 4 different resonance structures are possible. Now we can think about the bond order. Bond order that is equal to number of bonds by resonating structures. Number of resonating structures. number of resonating structures. So number of bonds here, you leave this K. So 1, 2, 3, 4, 5, 6, 7. Right. So actually if we count like this, 1, 2, 2, 2. So total number of bonds is 7. That equal to 7 by number of resonating structures 4. That is equal to 1.75. So this is a bond order for M1O4 minus 7. This is a bond order for M1O4 minus 7. This angle remains tetrahedral due to resonance. So remember, this is important. They'll ask for the bond angle by giving a compound which is having the tetrahedral structure. So you have to identify the structure of this compound and then you have to identify the bond angle. The angle remains tetrahedral due to resonance because the bonds keeps on changing. Here now it is single bond here, and next time there will be single bond. Here it will be single bond on negative sign, and next time here there will be negative sign single bond on here there will be negative and single bond on this side. So the bonds keeps on changing. So thus the angle remains constant here. Bond order is nothing but M1O, the number of bonds by the total number of resonating structures. So as I said, 2 bonds here, 2 bonds here, 2 bonds here, and 1 bond is here. So 7. Number of resonating structures we already seen 4. So it is 1.75. Then we can go for formal charge calculation. Calculation of formal charge. Formal charge calculation. What is the charge present here in the M104 minus? M104 minus. The charge present here is minus 1. Right. The formal charge calculation is nothing but charge, that is a total charge divided by number of resonating structures. Number of resonating structures. Total charge divided by number of resonating structures. So that is equal to minus 1 by 4, that is equal to minus 0.25. So this is a formal charge of M1O4 minus ion. Right? Yes. Formal charge is equal to total charge by total number of resonating structures. So that is minus 1 by 4, that is equal to minus 0.25. Next, the KMnO4 behaves as a self-indicator in various situations because we know that while doing the titration in lab with KMnO4, no need of indicator. No need of indicator. Why? Because it is a self-indicator. It itself acts as an indicator, right? And it gives permanganic acid. Write down the formula. That will be helpful for you. HMnO4 permanganic acid. So it is a weak acid, but it behaves as an oxidizing agent. It is a weak acid, and also it behaves as an oxidizing agent. Preparation of KMnO4. So the KMnO4 can be prepared mainly by two methods. One is from M1O2, that is called as pyrolusite ore, and another one is from H2S2O8. This is called a peroxydisulfuric acid. Let us check out in detail. Right. First part, that is from M1O2, that is pyrolusite ore. This is called as pyrolusite. Pyrolusite ore. This is brown black in color. Brown black. This is brown black, and this M1O2, that is a pyrolusite ore, when it is treated with potassium hydroxide and oxygen, it gives K2MnO4. K2MnO4 means here it is in plus 6 oxidation. It is not KMnO4. This is K2MnO4. So this is dark green in color. This is dark green in color, which when subjected to electrolysis, it gives M1O4 minus. That is, here it is in plus 7 oxidation rate. M1O4 minus plus M1O2. Right? So this is the thing. What happens here to the K2M1O4? Here, what happened? This is the oxidation state. What is the oxidation state of M1 here? This is plus 4. So from plus 6, it has gone to plus 7. From plus 6 it has gone to plus 4. So oxidation state increases. So this reaction is called oxidation, and oxidation state decreases, and this reaction is called reduction, right? So oxidation reaction and reduction reaction takes place in the same thing, one. And one element, that is one element exits in three different oxidation states, plus 6, plus 7 and plus 4 in this reaction. So this reaction is called as disproportionation reaction. Disproportionation. Disproportionation reaction also. Got it? That is MnO2 when treated with KOH in oxygen, it gives K2MnO4. The K2MnO4 when treated when electrolysis, it gives MnO4 minus and MnO4O2. Right, let us go for the clear version here. MnO4 is pyrolusite, as you know. Here, this is a pyrolusite actually, brown black in color, and this when treated with KOH and O2, it gives K2MnO4, which is dark green in color, which is electrolyzed. It gives MnO4 minus and MnO2. So oxidation number increase is oxidation number decrease is reduction. So the oxidation reduction taking place simultaneously, and an element exhibits in three oxidation states. That is plus 6, plus 7, and plus 4. So this is also called as disproportionation reaction. Right. The first method of preparation is also called as disproportionation reaction. So this is the first method of preparation. This is called a disproportionation reaction. Let us go for the second method here. Second method of preparation, that is from H2S2O8, peroxy disulfuric acid. So this is called as peroxy disulfuric acid. Peroxy disulfuric acid. So what happens here? Actually, we can write it as an ionic equation. S2O8 minus 2. Right. So this is the ionic form. So this breaks like this, 2H plus plus S2O8 minus 2. So this, when treated with Mn2 plus. Mn2 plus means we can go for MnO2. Right. Mn2 plus water, it gives MnO4 minus plus H plus. So what we have to understand, the S2O8, yeah, the S2O8, what happens here? This gets converted into SO4 2 minus, SO4 2 minus, and the Mn2 plus has converted into MnO4 minus, that is from 2 plus to MnO4 minus, that is plus 6 oxidation state. So from 2 plus to plus 6 oxidation state. Let me write the equation here, that is H2S2O8 plus MnO2 plus H2O gives HMnO4 plus H2SO4. Right? So what happens here? This is an unbalanced equation. We have to balance it. What we have to understand here, the MnO4 gets converted into HMnO4. This when treated with the KOH will use KMnO4. Right? This when treated with KOH will give KMnO4, and this the peroxide sulfuric acid gets converted into sulfate H2SO4. Clear? Right. Let us go for the clear equation here. Yes, this is a clear equation. Mn2 plus when treated with the S2O8 minus 2 minus in the presence of water, the Mn2 plus gets converted into Mn7 plus 7 plus SO4 2 minus plus 3. And this is an important question. So where does the acid, that is peroxide disulfuric acid, H2S2O8 is derived? So that is from peroxide disulfuric acid, and this is also called as Marshall's acids. And this is also called as Marshall's acids. And in some question papers, it asks for the structure too, for the Marshall acids or peroxide disulfuric acid. So it will be H2S2O8. Na? Right, you have to understand a simple thing. There will be two oxygen between the two sulfur, right? And two hydrogens over there. Na? The OH are attached to the sulfur atoms. Then one, two, three, four sulfur has been given. So another, sorry, four oxygen has been given. Another four oxygens over there. So put it in the sulfur atom with the double bond. Double bond O, double bond O, double bond O, double bond O. So this is the structure of peroxydisulfuric acid or Marshall's acid. Peroxydisulfuric acid or Marshall's acids. So this is H2S2O8. And another acid will be asked for you often, that is called Carr's acid. Carr's acid. Carr's acid. That is nothing but H2SO5. That is Carr's acid. The structure will be SOOH, and here on OH, double bond O, double bond O. So this is called the Carr's acid. H2SO5, Carr's acid. So Marshall's acid and Carr's acid, that should be in your mind. Let us have the clear structure here. So this is called a peroxo linkage. Both things. This is called a peroxo linkage here. So this is called Carr's acid or peroxy monosulfuric acid or persulfuric acid. And here this is Marshall acids or peroxy disulfuric acid. Right? This is peroxy disulfuric acid. This is peroxy monosulfuric acid. So here this is a peroxo linkage. This is a peroxo linkage. Got it?